11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Okay, we got a roll program.
Neil Armstrong reporting the roll and pitch program.
I'm going to show you a lot of stuff that if you try to answer the questions to, get into math. And as you get older, you can say, oh, this is a cool part of rockets. Now I know how they do this. And we'll talk a little about that.
Can I pull out a notebook so I can write them?
Oh, absolutely. You want to notes and stuff? By the way, I will put these slides up on the net someplace so you can download them and you watch them at home on your computers if you want. It's mostly just rocket launches. I went through YouTube and got some various interesting things going on. And so I could show you and explain to you what's going on with a rocket launch, because it isn't just a big fire and a thing going in the sky. There's a lot going on, and you guys are old enough to understand what that stuff is, at least a lot of it. Okay? Any other comments? No? Okay. So people call me Ches. I've been a science guy since I was about your age. That was back in the 1950s. And the world was an amazing place. We had new stuff. We had rockets going up. We had atom bombs and nuclear power. Lasers had just been invented. The idea you could buy a laser in a drugstore was crazy. These were in labs and stuff. There was a lot going on, and the rockets started going up, and I wanted to learn more about it, and I got interested in science and sort of became a science guy. That was 60 years ago, and I can tell you, if you're a science guy or girl for 60 years, you'll learn a heck of a lot of science. And I thought I would take some of what I've learned and show you what's going on with rocket launches. And I thought second graders, fourth graders, they can handle this. They know what's cool. Rockets are cool. So that's what we're going to do. So let's start with what rockets were like when I was just getting into this. Because rockets had a lot of failures. Come on, you can start now. Do I have to tap this, honestly? Is that what you're going to make me do? There we go. Rockets were brand new, and things went wrong with them all the time. By the way, you can add sound effects if you want. Here's a rocket going up. Good.
Oh, no.
You see how it's going sideways? Rockets do not like to go sideways. Okay? How about this one? Rockets need to have enough power to get off the ground.
Oh my goodness.
Otherwise, they do that. Boom.
Oh my God.
Yeah.
People have died?
No, there were no people in any of the rockets you're seeing here. However, yes, people have died in rockets. It's scary. Look at that one. Looks like the combustion chamber broke open. That not only destroys the rocket, it destroys the launch pad.
I only have to build a whole nother.
Yes, you do. And we're going to look into that a little bit. Let's see. Okay, here's another one. Good. It's going up. Ooh. Oh, it's not. Now you notice rockets have to steer themselves, but this one's not doing a very good job of it. And another thing is rockets don't like to go sideways. Then that happens, and all that rocket fuel blows up.
It looked like it was spilling like blood.
Yeah, it was, but it wasn't blood. It was rocket fuel.
It's red.
And this guy, oh boy, that died very early, didn't it?
It's like it was trying
Now,
to make a rainbow.
these are really expensive, and it's hard to do, and I'm going to explain how hard in a moment.
Are you gonna see like a one that actually goes up?
Yes, we have much more successful launches later, but I wanted to show you, this is what rockets did when I was a kid, a lot. Yeah, that one sort of didn't get off the ground.
Wow.
They're cool in the movies, not in real life.
Yeah, well, that one, I'm not sure what happened there for a little while. I think the top part came off, went up in the air, broke into a piece, and then the rocket's now shooting out of both ends because it's just a tube with rocket fuel in it now. That looks sort of strange, doesn't it? But wait, there's more. And then over here, meanwhile, at the rocket launch, the first stage is still sitting there blowing out of both ends. Okay? All right, so I think we've seen enough of those. If you want, you can see all of these and a lot more if you go to YouTube and type in the right words for rocket explosions or rocket launches. You can, there are hours and hours of this stuff, and this is just giving you a taste. Yes?
I've actually heard on Facebook that there have been self-landing rockets.
Yes, we're going to see a little bit of that.
The rocket thrusters.
Yeah. We're gonna talk a little about that. Yes.
I've actually seen a real rocket.
Did you go up in the air?
No, in the Air and Space Museum.
Yes.
Oh yeah.
Yeah, that's right. They have them there. And when we're done with this talk, you're probably going to want to go back to the Air and Space Museum and look at the bottom of the rocket, because the rocket has to steer, right? That means that rocket engine has to move around, or they have to put something in the rocket flame to move it around. And you can look underneath the rocket and see how it gets steered. And that's something I do at the Air and Space Museum. But I'll tell you, it is much more awesome. Yes, it is cool, and you should do that. Much more awesome to actually see them going up into the sky. And I hope you do someday. But let me explain a few things about rockets. There are basically two things that matter getting to the math of this. How strong is gravity, and how much energy is there in rocket fuel? Because if gravity is too strong, or if rocket fuel doesn't have enough energy, nothing goes into space. And if the Earth were 5% bigger, that's not much, none of our rockets would work.
Really?
Yeah.
Why?
Because there isn't enough energy in any of our rocket fuel to get it up there. You see, the big deal with a rocket is you're spending most of your rocket fuel to get more rocket fuel up into the sky, right? That's why we have a first stage with lots of it, and then a smaller one, and so on. And as a result, we usually can't get more than about 15% of the weight of the rocket into orbit, and usually less than that, because most of the energy we're spending is to lift other rocket fuel up to get where we can use the rocket fuel. You getting this?
Yes.
And that's an equation, and there's math involved with that. But the point is, unless we have more energy in the rocket fuel. Oh, how many have seen the Estes rockets? The little things you light and they go shh.
Yeah.
You seen those?
Oh, yeah.
Do you know what the rocket fuel is in those? Gunpowder.
Oh, I was gonna say that.
Well, you were right. And do you know how big a rocket you'd need using gunpowder to get into orbit?
Like tons.
No, you're way off. If the entire Earth were made of gunpowder, there wouldn't be enough gunpowder to get into orbit.
Wow.
Gunpowder does not have enough energy to lift more gunpowder into orbit.
Wow.
So early on, one of the books I read recently was about the scientists and chemists who were taking really reactive high energy chemicals, trying to figure out what can we put together to make rocket fuels that will work. And you not only wanted to have high energy, which means they might blow up, but you'd also like to have your rocket fuel not be poisonous.
Right.
And you'd like the flame that comes out not to be too poisonous. And some of the really best chemicals are deadly as heck. So that is an issue as well.
Wow.
Okay, so when I tell you that the Earth almost is too big for rockets, that means, this should tell you something, that we as rocket designers means we're going to have to, we really have a challenge. We're right on the edge of something not working at all. That means we're going to really need to make the rocket just right with high-powered stuff and lightweight and really strong, because it almost is not possible to do. So we're going to take a moment and think about how a rocket actually works. I want you to each imagine that you're in a chair with wheels on it that rolls really easily. Okay, that part's easy.
Office chair?
Could be. I want it to roll even easier than an office chair. Maybe it's sliding on ice. This is a thought experiment. Now I want you to imagine that your throwing arm is a giant gorilla arm with a massive shoulder and really big muscles and a big hand. Okay? Okay? Yeah. And you've got in your hand a bowling ball.
Oh.
Okay? You sit in the chair and you take your massive gorilla arm and throw the bowling ball really hard that way. Which way do you go?
Back.
Backwards. The faster you throw the bowling ball, the faster the chair goes back. Now, after that bowling ball leaves your hand, is it affecting your chair at all?
Yes. Yeah. Yes.
After you've let go, it's flying through the air?
No.
It's gone. It might crash through the wall and crash into your car outside. You don't care. You're still rolling the same speed. The point is the bowling ball does not, the fact that you're moving is not because the bowling ball is pushing against the wall or the car. It's that you were pushing against the bowling ball. And so when people see a rocket launch, those who don't know what they're talking about will say that the rocket goes into space by pushing against the ground. It doesn't. It is true that the exhaust pushes against the ground and it makes a big mess of the launch pad, and we're going to talk about what that part does, but that has nothing to do with what makes the rocket go. In fact, the rocket goes better in space when there's nothing stopping the exhaust coming out. Okay, now rockets, let's take the bowling ball one step further. Supposing you have a lap full of bowling balls and you throw it, you'll go some, but the bowling balls in your lap don't let you go as fast. So you pick another one and throw it, and you keep throwing bowling balls until that last bowling ball is only pushing you. So it's a multi-stage bowling ball rocket, okay? Rolling along there with a bunch of angry people where you've thrown the bowling balls at. That's Newton's second law, and that is what makes rockets go. Except obviously rockets don't use bowling balls. We use things much smaller. In fact, the smaller the thing you can use, the more efficient it is. So we throw atoms and molecules. And we throw them a lot faster than the gorilla can throw. Yes?
Actually, I have a Wednesday night thing,
Yeah?
and this week if the weather is good,
Yeah?
we're going to be launching rockets.
Cool. But those will probably, unless you're doing rockets up to C, those are all gunpowder rockets, which is fine. If you go up to the D rockets, they start using other stuff that's more efficient. But getting back to the bowling balls, the rocket throws atoms and molecules, and it throws it at about 10,000 miles an hour. That's 10 to 15 times faster than a rifle bullet. And the faster we can get the rocket to throw stuff, and the more stuff we can get it to throw, the better the rocket works. Yes?
So then it's kind of like a little toy one where you use water, like you push
Yep,
down and then...
yep, that's right. Except the water one doesn't have nearly enough power. It squirts out, it lifts it up a little way, but we're going into orbit. We have to go 5 miles a second when we're done, which is really fast. Okay? So the whole idea of a rocket is you need to throw a lot of stuff really fast. To do that, we make a combustion chamber with a hole in it. And we have to have inside the chamber really high pressure so that it comes out really fast at low pressure. To get it really high pressure, we have to burn something. And to burn something, that means we've got to pump something in that burns, gets really hot, makes a high pressure, and then comes rushing out. And that's how a rocket engine works. But since rockets almost don't work, that combustion chamber has to be really hot and really strong and not very heavy, because it's one of the things we got to lift up into the sky. So it's really at the edge of engineering, and that's why most of those rockets died. Because people were trying to figure out, we need more, or we need better metals and stuff. Also, the temperature in there is something like 3,300 degrees. Most metals melt at that temperature. You don't want your rocket melting while it's running. Yes?
But if like humans were in there, then...
Well, humans are up at the top when you're humans there. And you can imagine how scary it is for the first humans who know that just 2 years ago, the kind of rocket they're on blew up. And you hope that the guys have fixed the problem with the rocket. And so being an astronaut is a bit dangerous.
Yeah.
Okay? That is what you do as an explorer. You may die going into space. And that is something you think about and you discuss and you say, it's totally worth it, or I'm not doing that. Okay? And the people who build the rockets and approve them, they all say, well, look, you're going to have to check everything a whole bunch of times in a whole bunch of different ways because we really don't want it to blow up.
Yeah.
Okay? They actually have some, I won't show you this today, on the early rockets, they had a rocket on top of the capsule. The guys are in the capsule at the top, and there's a rocket at the top, and if the rocket underneath blows up, that one pulls them up into the sky instantly ahead of the explosion and dumps them in a parachute and lets them land.
Wow.
We never actually had to use that, but it was there for that reason.
Smart, they should do that on these.
Well, we don't, actually the new SpaceX Dragon capsule has rockets in the top so that they could do that, just in case. but we don't want it to explode in the first place. Okay, so let's take a look at Apollo 11. This was the first trip to the moon. Okay, this is a close-up, slow-speed camera of the bottom of the rocket. These rockets were Saturn V rockets.
What year was this?
This was 1969.
My nana was born.
And all the world who had TV watched this launch. This is really slow motion. Okay? Now, these things right here, they're holding the rocket down. You don't want to let go until the rocket's at full speed. And we will watch them go. This is just starting up. You have to put stuff in there. Now, there's a problem when you first start a rocket.
Whoa, that
Yeah, that's right. Now, you notice it's not going down, it's going up. This is all the rocket fuel and the oxygen starting to burn as the engines, oh, the engines just started. They're starting to shoot down and they're sucking all that stuff through there. Now watch, it'll clear right up because they're about to be the world's biggest blowtorch down here blowing down. This was the largest rocket engine, 5 of the largest rocket engines ever built. And you can see they're just starting to come up to speed. It's also a giant blowtorch. It is going to completely flame this whole area. And we want to use this rocket pad again. In fact, it's still around, which means they have to do stuff to the pad so this doesn't just burn everything up.
Right.
In fact, these guys, which are holding the rocket down, will actually lean back and get under cover because this is going to be under the blowtorch. You can see it's just starting to go. By the way, all that fire is going down into a special trench and shooting off sideways. It is pushing against the ground, but that's not why the rocket's going up. And all this stuff falling off here is ice coming off the rocket because it's full of liquid oxygen. Yes?
But like, and not in slow motion, how fast would it be?
Oh, a few seconds. We're going to see some launches in real time. But you're seeing a lot of detail here. This is about 15 times slower than real life. There is the rocket engine coming out. You notice how that's dark?
Yeah.
Well, this is a blowtorch. How come this nozzle doesn't melt?
Whoa.
It doesn't melt because they took some of the cooler stuff and let it run around the outside. I have seen a rocket launch. You know, this looks bright.
Yeah.
If you're actually there, you can't look at it. It's like looking at the sun. It is that bright. And that's even if you're 5 miles away.
Wow.
Okay?
5 miles away, you still can't look at it?
No, it's too bright. It's a really bright spot.
How are we looking at a ball of fire going up?
It's like fire, and I'll show you this.
How are we looking at it now?
We're looking at it through a camera. The camera can only get so bright.
And the ground shakes.
Oh,
The
the
ground is
noise is awesome. In fact,
it's just
the
like-
noise will damage the launch pad. And it is that loud. And so what they do is they spray tons of water on it to keep it cool. Well, the water boils instantly. And the sound breaks up the water droplets, and that makes the sound less. Wow. I have watched a shuttle launch from 3 miles away, and it shakes your guts. I have watched a shuttle launch from 11 miles away, and it shook my guts so much. It was my first launch. I said a bad word. If you're watching it from 11 miles away, which is just fine, it takes over a minute. It's going up for a minute before the sound arrives.
Wow.
And you're sitting there and you're saying, this is amazing, and then suddenly, now you see the rocket is now above the launch pad, but all of this stuff is down here and it's burning stuff. They put a special paint on here that's supposed to come off and burn off, which will protect the stuff underneath.
The blue is more intense.
Okay, so let's move on. How are we doing? We're doing well. Okay, good.
Now that blue color is like a more intense fire, more intensity.
No, the most intense you saw was the white there.
The white.
The white, the blue is actually hydrogen burning.
Okay.
And you can see little colors like that in a fireplace fire. It's a hydrogen burning. Yes?
Wouldn't the camera be like really shaking?
Yes, it would not only be shaking, it would be melted. That camera was behind a quartz mirror. It was in sort of a little armored place that could withstand this. And even so, it got a whole bunch of water and stuff on it. Yes?
When we had a bonfire, a control,
one, and my uncle bought like this can of stuff that's supposed to make your fire rainbow. It's probably a bunch of chemicals, and we shook it on, and it was a green and blue fire.
Okay, we're going to get back to that because you're going to see some rainbow, a little bit of rainbow chemical in another launch. Yes, you're next.
What's your last name?
Cheswick.
Okay.
Cheswick. You had a... No. Okay, you're next.
Can I go and drink some water?
It's fine with me.
Teachers. Teachers.
Teachers, ask the teachers. It's fine with me. We're going to keep going though, so you're going to miss something because we're doing the space shuttle next.
Ooh. Oh my gosh.
Okay, all right, first of all, this is underneath the space shuttle.
Just real time?
No, actually, this is slow also. Okay, first of all, I was thinking about this on the way up. No. I don't want it to stop. No, we're not doing that. I want to look at, you see those little sparklies? I was thinking about that. They're kind of pretty, aren't they? This is a little thing that shoots sparklies over here. Why is it doing that? It's doing that because one of the rocket fuels is hydrogen, which burns when it's in the air. And if you have too much hydrogen that isn't burned, it will explode. So you want it to burn quickly. So they have these pretty little sparkly shooting stuff. And it occurred to me, first of all, I don't know what the sparkly shooting thing is called. Okay, it's a sparkly shooter. Some engineer had to design the sparkling shooter. In fact, some 4th grade kid was going to grow up to be the engineer that would shoot the sparkly stuff. But if you'd ask that person, what are you going to do when you grow up? I'm going to protect a rocket by shooting sparkly stuff around the launch engine. Oh no, there wasn't a space program when that kid was in 4th grade. I don't know how that sparkly thing works, but as a science guy, I want to know, first of all, what's it called? It's not a sparkly shooter. It's probably a hydrogen pre-ignition suppressor or something like that.
Something with a complicated name.
That's right, but I'm going to go home with Google and try to figure out what that sparkly thing is. I want to see if you're making a rocket going to the moon, somebody somewhere said, oh, we got pre-ignition problems. Did they already know where to get sparkly suppressors? Could you go down to Best Buy? Probably not, but maybe they needed sparkly suppressors 10 years before on rockets? Or maybe they used them on jet engines. Oh, you're going to need a Rockwell sparkly suppressor on this. I want to talk to the people who designed it. And there's some old guy around who was on there. How much does one of those cost? Does it get destroyed in the launch and they have to put a new one in next time? What were they told were their hard parts? What is actually coming out and burning?
It's probably sparks.
Well, yes, sparks of what? See, I want to get down to the engineering. Is it carbon? Is it iron filings? Is it sodium metal? I don't know. I'd like to know what it is. But go back to that 4th grade kid again. The 4th grade kid, supposing the 4th grade kid knew he was going to grow up to be a sparkly suppressor manufacturer. So now someone, what do you want to be when you grow up? I want to do the sparkly suppressor for a moon launch. Okay, I meet a few people like you now and then. What are you going to do for your science project? I'm going to build my own sparkly suppressor. Oh yeah, you're going to make one of these in your basement? You think mom's going to approve? I mean, clearly there's fire involved and stuff. And then it occurred to me, I thought of this while I was driving up. Actually, as a kid, I didn't do a sparkly suppressor. I had a couple projects that I worked on that my parents did not understand that were quite dangerous. Now, I was careful to look up things and understand what I was doing. And I have all my fingers and my vision. But I met some guy once who made nitroglycerin. And where did those fingers go? He was a teenager who made nitroglycerin. Turns out it's not that hard to make nitroglycerin. It's a very touchy, high explosive. I don't suggest you do it.
So that's how many fingers he had left?
That's right. These were burnt off. Well, he made a bunch of it. I mean, that's really stupid. And it just exploded in the room, and he could have lost his vision and stuff. But it's sort of a sparkly suppressor, isn't it? Yeah. Now, on the other hand, the stuff I worked on, I learned a lot of chemistry. And I have talked to Nobel Prize winners in chemistry who did dangerous stuff like this when they were teenagers. And they were the ones who ended up with all their fingers. So I'm just saying that this can happen, but you also don't know what the jobs are going to be in the future. The stuff I did in my career, that job didn't exist when I was in 4th grade. Yes.
What are those numbers for?
Oh, that's a fine question. I don't know. Let's take a look.
It's the countdown.
No, it's not counting down. It's counting up, actually. This is 9 seconds after ignition. Maybe. Yeah, 10, 11. Oh, it reads backwards. See, 1, 2. Yeah. So this is telling when it's happening. And you're seeing here 3 of these shuttle engines. Now, one of the things that happens, remember that combustion chamber is high pressure? And you want to pump a lot through it? They have pumps on here that take the fuel and pump it into the chamber. That's taking low pressure into really high pressure, as high as we can get it, and lots of stuff. One of the pumps that fills that chamber can empty a swimming pool in 2 seconds. Gives you an idea of how powerful it is. Which, if you were a science guy, you would say, wait a minute, that takes a huge amount of power. How do you power that turbo pump? And the answer is they have a special little extra rocket engine inside burning rocket fuel that just runs the turbo pump. It doesn't come out here. You see these make nice little cones of fire? Also, you'll notice that this is clear. Liquid fuel rockets burn very cleanly. And you can look at a rocket going up and see that it's liquid fuel because it's pretty much just flame and no smoke. Solid fuel rockets like that one and the one over there make a lot of smoke. Yes?
If you noticed, if you look right there, you can tell that, look, the sparkly suppressor
It's still running, isn't it?
Yeah, it's still running, but you can tell it's slowing down.
Well, so it only has to run until the engines start. Now it's just extra. And, you know, the engineer is probably told your sparkly suppressor has to run for 15 seconds. Okay. Now it's taking off. And what happened was they lit the solid rocket booster. And you can see that really bright.
My eyes.
Yeah, well, you can't see, you can't look at it in person. Really bright and really smoky. Yeah, wow was right.
It's hurting. How's the camera guy looking at it?
There's no camera guy. The closest person to a shuttle launch, I've been next to him, is 3 miles away. Because every once in a while these things blow up. The fire engines to save people is 3 miles away.
So they're zooming in?
No, there's a camera built at the bottom in this little bunker and it's all automatic. And there are wires underground that let them do this stuff. Okay, you can see it's even shaking. This is the noise that made me say a bad word, but of course it's right next to it. Yes?
Like, what's it called? Would you have to use those, like, glasses that people use to, like, when, like...
No, it's sort of like the sun. You look and say, that's too bright to look at. You don't need special glasses to not look at the sun, or to know that you don't want to look at the sun. If you wanted to look at the actual launch, yeah, you might, but all you'd see is a white, hot hunk of fire, right?
And then your eyes would start hurting.
Well, yeah, it's a little uncomfortable. So here's an actual space shuttle launch. Okay?
Not slow motion?
Nope, not slow motion. We're going to wait 30 seconds. There's no sound for this. This was the last space shuttle mission. You can see here's the solid rocket booster. A big, that's the solid fuel, and we'll see that. This is the fuel tank, and those 3 engines down there with the swimming pool pumps are down there. They're ready to go. They start up early. Oh, they've turned on the water. This is to suppress the nose. They got the sparkly suppressors going like crazy. There it goes.
3, 2.
Look at that. Oh, you notice how those move? That's how it aims the rocket. Okay, all the smoke, almost all the smoke is from the solid booster. And this, you see the liquid is clear.
Excuse me, you
Yeah.
see the thing that looks like they're not supposed to be attached, but the red thing, doesn't that...
That red thing is a fuel tank.
Yeah, doesn't that break off in space?
Eventually, yeah. In fact, because you just getting a little bit of something into space, you throw away all the weight you can. And the first thing you throw away is the solid rocket boosters as soon as they're done. Because there's no reason bringing an empty booster into space. So we throw them off. That's going to happen pretty soon.
Wait, but if there's like, when it's falling, does it just like fall off?
It falls off.
But like, where does it land?
Where does it land? Good question. This place is located on the beach in Florida, and they launch over the ocean. And those things fall into the ocean.
Oh, okay.
Okay?
I was like,
They
it's
don't
just
in
like-
Russia. In Russia, they launch in the middle of a giant continent, and they fall someplace in Kyrgyzstan.
It's like if somebody's like, oh.
Yeah, could happen.
Every time.
Yeah, yes.
It's my house, not again. I was kind of wondering Is that like, is it kind of looks like a plane, but not really?
It is.
Oh.
And in fact, the whole idea of the shuttle was after they're done in space, they would slow down and then they would fly in and land. So you could use it over again.
Oh wait, and another question.
Yeah.
Wouldn't it be hard to like, cause you're in space and then you have to come down to Earth? Wouldn't it like make something like?
Like fire?
No, like yeah.
Like what?
It's kind of like
It doesn't crash.
Like- like, and it's coming down from
Yeah.
like space really fast.
It is. But it leans back and eventually it glides. Well, it sort of glides like a brick. It's not a very good flight. But it comes down and you can see landings if you want. Go on the net, look at shuttle landings. Wheels come out and it comes down and it lands, and every one of them landed just perfectly. They got down that far. Okay, we got 2 more, then we got a lot to do. You're first.
Have some people actually been killed by the empty rocket boosters that fell
No.
in Russia?
No. Not that I know of. If it happened in Russia, they never told anyone about it. But usually, and actually China has the same thing. Their boosters fall somewhere in the middle of nowhere. Usually these things are away from people, though I do know of one rocket that was launched by the Chinese that went and wiped out a nearby town.
Oh my gosh.
That's what they did. Okay, last question for now.
What year was this?
I don't remember. This is the last launch. It's STS-134. If you remember that, you can look it up and find out when it was. Because
what
this
is
was
that?
the last launch, STS-134. That's the last space shuttle launch. We don't use them anymore. And you can see one at the Airspace Museum and other places too. I got to keep moving here, guys.
Oh
No, you haven't unanswered question. Okay, what's the question?
Okay, so the when that launches, like, it kind of just turns into that small, like, plane there.
Yes, the solid rocket.
And the 2 fuel tanks, or the...
The 2 guys on the side are the solid rocket boosters. They get it going and they fall away. And if you're watching from the ground, you can see them fall away and go into the ground. This doesn't happen very high up. Then
2011.
this
Yeah.
part, good, May 2011. So that was 7 years ago. We're never flying them again. And this guy uses those shuttle engines that we were talking about with the tank of fuel, and that goes up, and then they drop the tank away, and that burns up in the atmosphere, and then it keeps firing with the rest of its fuel, and it's in orbit.
Will we see?
And then
Will we see the tanks fall here?
You will see these, since I'm not stopping it, you will see the SRBs, the solid rocket boosters, come off. Okay? And this is what it looks like. It's a giant column of smoke with an unbelievable amount of noise. When the noise gets, remember, noise goes 5 seconds a mile. You know how you see lightning and then thunder comes later? Well, you're at least 3 miles away from this, and that's if you're lucky. If you're in Titusville, you're 11 miles away. You don't hear a thing for about 65 seconds. And then as the launch sounds finally reach you. Meanwhile, this is way up in the sky. And you can see its altitude. It's already at 23,000 feet. It's going 800, it's faster than a bullet. So there's something else that's going on. When you watch a launch, they talk about something like, we've now reached max Q. And they always mention this. They always mentioned it on the shots when I was a kid. And so as soon as this is done, I will explain to you why max Q is a big deal. Because it has to do with our designing a rocket to work. Okay, there it is. The SRBs are going. You can see they're really bright and they're getting smoky. You also notice the fire's getting wider. We're going to talk about nozzles next, because that's important. You see that because there's less air and all that pressure isn't going straight down anymore. It's going out sideways more. And when it goes sideways, it's not pushing the rocket up, it's pushing sideways. So we put a nozzle around that to make more of it go down. And the problem is that this rocket goes from sea level, lots of air, to up high where there's almost no air, and the nozzle isn't the right shape for all of them. So they have to pick a shape that sort of works the best during most of the trip.
Wow.
Okay? So, and you see they all get the big plumes like that, and that's what's going on. Now watch, here we go. The SRB is just about done. Boom. Okay, we're seeing them separate from up in the sky. That's nice. See, that's what they look like. Meanwhile, those 3 engines keep going, and the fuel tank, and it's going on.
Is it still in the atmosphere right now?
You know, it's so thin up there, I wouldn't, you couldn't breathe it. Well, here, wait, we can tell. It's at 100,000, 200,000 feet. No, you would suffocate in a minute up there. There's practically none up there. Yes, there were 7 astronauts on board that.
Wow.
Yeah, can you imagine what the ride is like? In fact, we can tell a little bit because there's a G-force on here someplace. Range, no, I thought I saw the G-force. The thrust, we're running at 100. Okay, so there we go. That's 2 minutes and 48 seconds into the launch.
Do you know when's the next launch?
Okay, so if you're interested in seeing more launches, go to Google and look for Worldwide Launch Schedule. Okay, that's all you have to remember. And it will tell you things from Cape Canaveral, things from Vandenberg in California, and Walp's Island in Virginia. There's a place 3 hours from here that you can go watch a launch. And whenever I go to Florida, I'm checking, because if I'm down there for any reason at all, I'll stay an extra day or two to see a launch. So I have seen 4 shuttle launches, 3 of them from down in Florida. I saw 1 shuttle launch from New Jersey. Huh? Well, the shuttle launched at night, went through all the rocket stuff, and was just the engine flying up the coast at night. And there was a school I stood at, and you could see a little light going along the sky, down near the horizon. It wasn't loud or impressive, but it was a shuttle launch, and the engine finished being in orbit when it got over around Connecticut.
What year was that?
That'd be about 1994. It's a long time ago. But no, well, all of this stuff. Okay, last question, then we're moving on.
It's actually not a question, but like that's the space shuttle I saw.
This one? Could be. Yeah. And now it's just museum stuff. It's kind of sad. But it turns out that the idea of reusing the shuttle is a great idea because we wanted things to be cheaper. I mean, think about those SRBs. They crash into the ocean. We don't use them again. Those rocket engines work just once. Yes.
They retrieve them?
They retrieve them, yeah.
Do they use the pieces from there?
Huh?
Do they take some of the pieces from there? That's what she said.
No, there may be pieces in the museum. I don't know. Of course, the thing Elon Musk is doing with SpaceX is he's reusing all sorts of parts of the rocket. Okay, so let's move on here.
You have 15 minutes.
Okay, here's SpaceX launch.
15 minutes.
Good. I think we're about right then. Okay, here is 12 SpaceX launches in a loop. And you can see there's fire coming out, and there's smoke, and you know, they're all starting, and then I looped it, so we get to watch it again. And the reason we're looping this is because rocket fuel has high energy. You take fuel, which in this case is kerosene, which is like diesel fuel, and liquid oxygen, which can start a fire in tenths of a second, and you put them together. And if you put them together without lighting them, they don't catch fire right away. And if you get just the right mixture, which rockets have, and then spark it, you get an explosion. And in fact, one of the biggest bombs you can get in the military is called a fuel air bomb, which comes in and sprays a giant cloud of fuel, and when it's just about right, it sets it off, and it makes a huge explosion. Now, as you can tell, because you're now experienced rocket engineers, we don't want huge explosions in our rockets. We want, as soon as the things come together, we want them to light immediately before it gets, okay? So it starts up gently like. The sparkles can help, though they use spark plugs and stuff in the Saturn V. These guys, SpaceX, uses something else. They use a compound, I think it's a boron compound. You've probably never heard of boron, and it's boron trimethyl boron. It is a compound that the instant it hits air, it catches fire.
Wow.
Okay? And what they do is they inject a little of it into the rocket engine just as it's starting up. And the cool thing, and one of the things I really want you guys to see, is boron, when it burns, is light green.
Oh, I saw it in number 5.
There you go. Well done, Kayla. I want people to look. We're going to loop through this, see which other ones have green in it. Yeah?
Right there.
There. Now
Number 1, number 4, number 5 all had green just there.
Yes, ma'am. Now you don't get to see it on every launch because they don't have the camera in the right place.
Number 8,
Well,
you can see a little.
You can see it on 8? Let's see.
Yeah, look.
Yes? Oh yeah, there's green in 8. Now they all use it.
1, 4, 5, and 8 all
Yep.
had.
They actually all use it, but the camera isn't always in the right place for it.
8 has so much.
At the very end, 9 has it.
Does it?
Yeah,
You shouldn't see it at the very end because it's the first shot. Yeah, I think that's something with the lens on number 9. I can see how you'd say that, and it does look greenish, but I don't think that's the boron. Okay, it really has to be right at the beginning. So if you watch a SpaceX launch, and they're 2 a month now, watch to see the little bit of green.
Number 5 has the most.
I think that's right, but that's mostly because that's where the camera is. So that's boron, okay? You don't know the chemistry of boron. That's okay, most chemists don't know the chemistry of boron. But it's kind of interesting, right? Now you could go look at the next SpaceX launch and see if the camera shows you the green.
That's so cool.
It is cool, isn't it?
1, 4, 5, and 8.
Yeah.
4 has so much.
Okay, let's see.
I like 5 the best.
What do we got? Okay.
Falcon Heavy launch.
Falcon Heavy launch. This is, I went down to see this. This happened in January. This is Elon Musk's new rocket.
Oh yeah, we watched it on TV.
Yeah, it has 27 rocket engines in it.
Does this
And we were there. We watched it go up. It was amazing.
Was it loud?
Not as loud as the shuttle, because those solid rocket boosters are really loud. The regular engines, not as loud. It was still, but it wasn't bad word loud. Okay? But it was impressive. What was loud is, you know, it goes up and the rocket had a big main rocket and 2 side rockets. The 2 side rockets slowed down and came back and landed near where we were. And they're coming back fast. So they had to slow down. So first of all, you could look up in the sky and see flames there for a little while as they came in. Also, they're coming in faster than the speed of sound. So suddenly it was a crack, 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 as the sound waves reached us. And they came down and landed. You can see lots of pictures of those landing.
was this past January?
Yes.
Recent.
Okay, you can go now. All right, I'll leave the sound on. Okay, so what's all this smoke stuff?
Let's see if we can see any green.
You will not see green on this. I'm sorry, the camera was in the wrong place, but I assure you there was a lot of green under there somewhere.
Is that keep everything cool?
Yes, that's because this is full of liquid oxygen, which is really cold. And that, you know, in the cold morning when your breath has a cloud, this is the rocket's breath. Okay, it's really, really cold. If you make oxygen cold, it becomes a liquid, which gives you more oxygen. And if you make that cold, so it's even colder, you get even more oxygen. They want as much oxygen on there as they can get.
9, 8, sub-booster ignition, 6,
5, 4, 3.
See, the green's long gone. They didn't show us the green. Okay, tell me, is it liquid fuel or solid fuel? It's liquid fuel. Because you see, there's a little bit of smoke, but it's nothing like what we saw with the shuttle. This is SpaceX
Is that
people.
what you saw? Is that what you saw?
I was far away, but yes, that's what I saw. SpaceX is a company, a private launch company that is doing amazing things. You should look them up. They are astonishing, and they're beating NASA at their own game. It's wonderful.
I mean, like, did you see that detail when it launched? Or did
No,
you just see it both
it's
times?
easier to see it right here than it is to be there in person. But being there in person, you're with a whole crowd full of rocket people and having a great time. Hang on, I can't hear anything.
I can read it for you if you'd like.
No, it's nice to have the cheering. Okay, here's Max Q. I haven't told you what Max Q is. We're going to stop this because that was the last point.
Vehicle is supersonic.
Okay, we'll get to Max Q because that's one last point that I think a 4th grader can understand. Okay, we got 2 of the side rockets. They're going to fall away.
We're past Max Q, the period of maximum
Yeah, could you mute
load
it?
on the vehicle. Next up, we'll be waiting for the side boot.
Okay, so when a rock is going really fast and there's no air, nothing happens. That's like a rock out in space.
Yeah.
When a rock is sitting on the ground and there's lots of air, nothing happens. When a rock is going really fast and it hits the air, what does it do?
Fine.
It burns up.
It
You ever seen a meteor?
Yes. No. Take that back.
Yes, I have seen a meteor.
Look how wide the plume is. You can see plumes from each of the rockets. There's very little air up there, so it's going out like this. And those nozzles were not designed to handle that altitude very well. So this is less efficient than it was. Our rocket isn't working. We have no choice. But you'll see the next stage has a really big nozzle to work in the vacuum. Okay, we'll watch this finish. Then I'll talk about burning rocks because that has to do with rocket launch. Look how wide that is.
What's max Q though?
I'm going to tell you that after we watch this disconnection here.
So this
Okay, they shut off. They're both going away.
Oh, I saw green.
Did you?
Yes, I did.
Okay, all right.
Yeah, I saw some green too. I saw some green.
Okay, they may actually do green there to start engines. I'm not sure.
I didn't see green.
See those two guys come back down. Now, was that all I recorded? Oh, okay, this is one of the rockets coming back. No, this is the big one. This is the second stage, so we'll see this in a moment.
Are these yours?
Separation.
Okay, so the middle rocket's getting cut off now. And then that goes away. This is the second stage, and that is the second stage vacuum nozzle. Much bigger to try to hold all of that going out, going back instead. And there's a whole math and science to nozzle design. See how hot it's getting? It's glowing. Okay, that's enough. Good. All right, so rock going fast, no air, nothing happens. Rock not moving at all, lots of air, nothing happens. That's a rock you have in your garden. A rock in space hitting the atmosphere, you get a streak of light. And if you've never seen one of those, August 11th, fine clear weather, go outside. That night usually has a lot of meteors. And if you wait, there's about one a minute. And you can watch this happen. August 11th.
I think I've seen one on
You probably have. I used to go to the beach on August 11th just so I could lie in the sand and look at meteors.
I should be going to South Carolina around August.
Okay, so let me finish this up here. So the rocket eventually is going to be going really fast. And it starts when there's no air, or when there's lots of air, or air, okay? So not fast, lots of air. The rocket's going faster, and the air is getting less. Somewhere in the middle, it's going fast enough to be a problem, and there's still enough air to be a problem. And afterwards, it's going faster, but there's less and less air. So there's a little point in there, which they call max Q, where the rocket is pushing the hardest on the atmosphere. And if we're designing a rocket, we don't want it to fall apart when that happens. So that all the rocket design inside has to be strong enough to handle max Q. So if you design the rocket and it's going through max Q, you're saying, I hope we did this right. Because occasionally rockets break apart at max Q.
Or blow up.
They can, there's still fuel left, but that's a little less often. Okay, so let's see, what have I got left? I'm just about out of time. This has worked great, hasn't it?
Yes, thank you.
That's it. Oh, yeah, that's it. Current slide 12. Those are the slides. So, did you like this?
Yes!
Do you think you learned some stuff about rockets?
Yes!
Does this sound like something you might want to work on someday?
No!
That's okay. You're allowed to say no.
Maybe.
But maybe you'd like making the sparkle generator. I don't know. Okay, or not. Maybe not. This is about as good as you can do at your age of figuring out what you want to be when you grow up. Is figuring out what's cool, what sort of stuff is cool, because you're not going to be able to pick your particular profession. It may not exist unless you want to be a 4th grade teacher. We'll be needing those, and you can do that. You can want to be one and be one, or veterinarian. There are some things, but a lot of the technical ones come and go over the years. And you have to be ready to figure out what you want to be when you grow up many times. I'm still figuring out that myself. So any other questions? How are we doing for time, man?
We're good. That's good to go now.
Good to
Thank
go.
you so much.
My pleasure. Thank you.